Welcome everybody, I'm Tommy White, heading the sales team here at MasterSeries in the UK. I'd like to welcome everybody who's joining us from around the world. At the last count, I think we had over 19 different countries, from as far east I think as the Seychelles and Singapore, and as far north as Denmark. I think is the furthest north that we got of people logging in. So thank you very much for attending. I'm going to first of all give you a little review of what the MasterSeries is, because not everybody is a user. So I'm just going to have a quick 2-minute PowerPoint presentation. Here we go. Product range. We have a massive range of products. The MasterSeries, it's a modular system for doing frame analysis, portal frames, simple beams. We can obviously add on advanced analysis functions such as wind, finite elements, dynamic, and even seismic analysis, and your BIM integration. From a design point of view, we have steel, concrete, composite, connections, and timber all in the system. And then we have some standalone modules for masonry, retaining walls, pile caps, RC detailing, and office. Now the pile caps and the RC detailing do integrate, in fact, but they're better handled down here. So that's a lot of packages, and there are a lot of different permutations and solutions. And to help you, we created these 3 suites: the Building Design Suite, PowerPad, and Masterport Plus. Big buildings, medium-sized buildings, very powerful and useful. For the smaller work, you have the PowerPad Plus, and then for specialist portal frames, you have the Masterport. And for people who don't come into any of those categories, you can build your own. So I'm not going to go into what each of these contains, but what I will do is just pop up a little diagram that tells you what we're going to cover. So we will be covering the Building Design Suite, steel design, so we'll be doing steel design if you're the Building Design Suite. If you have PowerPad Plus, we will also be covering that. So each of these programs will be covered and is suitable for doing steel design. Or you could come along and take your frame analysis with your steel design only and no additional products. What I will point out is that the basic 50-member version is not suitable. You would need the Pro to get the best benefit, and we will be using all the Pro features throughout to do our design. So let us, without any further discussion, get straight in here. So MasterSeries 2019, I'm going to start the software, and I'm going to be using my big network license, and I'm going to start now. So here we come into the system, and we can see the different types of frames we can do: frames, portals, flat slabs, the different types of standalone design, and the simple beams. I'm going to go into frames, but luckily for me, I don't even have to do that. I've already prepared the file. So let's look at the file we're going to start with. And we're going to spend 5-10 minutes looking at all the different features in it, looking at what we need to set up for this. So I have taken this in Blue Peter style from Revit and brought this model in, and it's got some basic section sizes, and we can see these are pretty constant. There's no rationalization of sections, just beams, columns, bracing, and a few trimmers and some haunched members. So the default sections. Now let's look at, I'm going to turn off the 3D coloring because it can get a wee bit annoying, and I'm going to go back to wireframe. It's just that bit prettier. We have introduced gravity area loading, and we're going to introduce our key, so we can see that we have dead load and live load, and we have self-weight on these floors. So these floors, the self-weight is considered separately to these dead and live loads, so we know what our values are. We can also drop this and tell it to include the slab self-weight, or multi-select and say give me slab thickness and dead end post. So I can see 175 and 225 slabs involved here. So 175 here with the shorter spans and 225 with the larger spans. So I can confirm my loading and just a 0.3 and a 0.6 live and dead and live on the roof. So just close that and take off that. So that's the basic gravity loading. And as you will notice, as I rotate around, we have a higher intensity here. What we've also introduced is some line loads, and these line loads are around the edges, but they're also in this area here for some sort of partitioning or something that's block work for fire and safety and whatever. We will also notice that over here where we have some openings for staircases, we have introduced a wall along here. We've introduced line loads here and here, and those line loads have been introduced to mimic the staircase coming up. Now we could create some parallel lines and put some area loading onto the stairs if we wanted to do that. We're doing it in the concrete structure, that would be possible, but we find this easier just to put a couple of line loads to mimic those values. Now, and I notice here that I'm actually missing a load on this area, so I'm actually just going to go in to loads, floor, line loads, and I'm just going to choose this line load here, and I'm going to say that I want to, it's on member placement, I'm actually going to add that and select this member here to put it on there as well. So that's put on, and you can see the high line load there from the stairs, the high out here from the stairs, but nothing here because it's just a single stairs from here up and then back, switch back. So it's nothing too complicated. There's no up and down stairs, it's all just the one set. We've also, just because we can, and I'll just turn off the line loads, introduce some patch loading onto 2 floors. So we put patch loading up here as well, again just to make the frame interesting and unusual. If we look at the plan of this structure, we'll see we've also introduced trimmers around the stairs. We've got some bracing at first floor roof level, and we've got bracing in these little cantilevers. Now we've also got bracing in the 2 sides and the 2 ends. So we're going to rely for first and second floor on the stability of the floor transmitting the loads back to these hard bracing points. Now we can do that quite easily using something called semi-rigid stiff deck. So I have taken this semi-rigid stiff deck and put loads here, and I've accidentally got one up there as well, which I'll just get rid of. It shouldn't be in the same category. Take that one out, and there we go. So that's that stiff deck. It's 175 thick, 26 Young's modulus, and then I go to the second floor and we'll see the solid floor. In this case we haven't left the opening for the staircase, and again I can very easily pick the 5 members, and it's now, and I got a bracing member there by mistake, remove that from the panel. Very straightforward, very, very easy. Now the next thing I have on this is that all of the beams are pinned. So what we've done is that we've taken all of the beams and I have pinned them. We'll see that in each floor we've got pins here. Now with this beam, which is basically a transfer beam from here and coming down here, we're putting in as one continuous beam, but everything else is simply supported, and we've just pinned the columns underneath here. The first floor is all pinned, other than that the second and third. So let's look at some of our frame views, and we'll see plant level 1, we can see our columns and our pins, but These beams, as I said, are continuous. Everything else is pinned with these being continuous, because that is the, you could say, the primary, the secondary and the tertiary beam. So solid the whole way across, then this one solid from here, and then the little simple ones. So again, that's all been set up very straightforward for us. And likewise, if we move up to the next level, it's the same scenario, and then into the roof we will see, putting it into front view, the bracing of the been pinned, plus all the eaves and ties been pinned as well. So that's setting up those, and I just click on the home and I get back to the full and turn off that. So we've set up our frame, we've got our bracing. Now we've also applied on this, obviously, wind loading, and I'm not going to go into great detail, but let's just say we've set up the wind loading on this in the 4 principal directions. So direction 1, and we can see our CP values. If we zoom in, the values 0.6 to 0.75 coming in there, 1.3 on the leading edge coming all the way down, and you'll also see that it is different on the back, because this is the leeward side, and that's just one direction of wind. And then we can say, let's look at the next direction where we're blowing here, and we get this leading edge here, and then we can see all the difference, and we can see all the different coefficients that are used in the frame. And we can then say, well, what's the actual pressures? In this example, it doesn't really matter where I've chosen it. So that's my basic loading applied. Very straightforward, very easy. That's not what this webinar is about. What this webinar is about is preparing this and designing it as a steel frame. So let's look at loading cases. We've got to introduce a whole lot of loading cases. And if I just go into the edit of the loading case generator, I can see that I can create all my dead and live and wind. So my dead and live, and I can see whether it's 610 or 16A and B, because we're in Eurocode, and we can say dead plus live plus wind. We can say favorable and unfavorable, live load only, dead load only, if you really want those considered, and we can pull all those in. So we can choose exactly what we want, and if you can see, obviously for live it's only the characteristic service, whereas for dead plus live we're dealing with this 610, but we're also dealing with the equivalent horizontal notional forces, and they will be applied as per the wind directions. So we have to put wind directions onto the frame to get that, but that again is part of just the wind analysis and not necessary to be taught here. So we've got our, in my case, 41 loading cases. If I go in and analyze this frame, static, we've got our notional horizontal loads, and we'll say space frame. Off it goes, and it flies through the 41 loading cases very quickly. Quick test. Let's look at the pretty diagrams to make sure we haven't got something totally stupid. And obviously it's going to be quite high in the diagrams, but yes, we can see the continuous beams here, we can see everything here, and I think always a good test is to look at the deflections with a very small magnification, and if we're getting roughly this member staying where they're meant to be, then we know we don't have an instability or anything stupid in the frame. So I'm happy with that. Now what I would do normally is go into steel design, steel member design, and I need to choose each of the design checks, and I'm going to say I want to do a beam and beam portion on that beam, and off I go, and I say, oh, it's going to be fully restrained because the deck's spanning onto it. And I can then come along and say, well, okay, how big will it be? And I can see that the fully restrained, is it fully restrained, or did I say one? It is fully restrained. Due to the deflection criteria, we need to work with a 305 by 67 kilograms. If I decided to work by weight order, I could get that down to a 457 by 52, slightly lighter, deeper, and probably actually in essence a better deflection ratio. So that is a better choice of section. And I can walk through and do that for every single member. I can even take that and I can suddenly say, well, let's copy that to and put this into front view, all of those beams, and maybe all of those, and all of those, and get some more design checks. Oh, I've just accidentally done the bracing, which is an example of why it's not necessarily the best way to do things. So looking at this, I've accidentally applied those to the bracing as well. It doesn't matter, I can delete those if I wanted to. And I can then walk through and do those, but that is a slow, laborious process and doesn't give us great control. And on very large frames, and this isn't a very large frame, that can become problematic. So what I have done is I have created an alternate file called with design groups, and we're going to look at where the MasterSeries design groups gives you that power to do your design very, very quickly. So what are design groups? So steel and composite member design groups. Design groups allow us to do things like those inner edge columns, all of them for the first and second floors. We're going to make them all the same section size. That's a bonus. And we're going to keep the data all the same. So we can turn around and alter the conditions. We can then do the same on the outer, and then on the upper, outer, and the inner. We can then do the same for each of these bays. So these transverse beams, we're going to say axial with moment, and in fact because of the hugging we probably want to do with Appendix G as well, because we're going to have a hugging moment over the top of the support. Never really a problem, but it's worth considering. And it's going to be restrained at the beam locations, and we're going to come all the way down. If we then look at our, sorry, going the wrong direction, internal beams at say first and second floor, inner beams here, we will see that we have included them as being fully restrained. If we then look at the transverse beams, if you think about them, these transverse beams aren't carrying much, but down below these transverse beams are carrying a lot. These are the primary beams. These primary beams are carrying a point load at the mid-span, or in some cases at third points. So what we're saying is we're not restrained by the slab, but we're only restrained at beams. So we've set up that this one will be restrained at this point and this point and this point, and the other ones here will be restrained here, here and here, because those three restraint points will give us restraint to the slab, and we can then check those all out. So I have set up a multitude of conditions, including obviously the bracing, and again I have set up that it is strut and tie. Now this bracing is a flat, so therefore I've put two web holes in at 22 mil. Quite important from a design point of view because of the net area effect. The bracing up here is CHS bracing, so circular hull section, so therefore we're not going to worry about holes because we have a cleat instead welded on. So the actual gross section is used in the strut and tie checks. For our rafters up here, we have a haunched rafter, and again we're dealing with Appendix G. What we've also said is that in this situation we're going to assume that we have restraints at 1.5 centers. So 1.5 centers along the member, we're going to have these restraints, and as always we're going to do the whole group in one go. So I have taken the time to go through and create them all, And if you want to see them all, there they all are. That's a very handy tool to see which ones you've done. Draw all. And I always like to do it with a nice thick line so you can see a good contrast between the members. So you can choose any member then and see, yes, they've been done, and they've been done. So there's no actual physical black member. I think this one at the back is the black one, is the one that hasn't been added to a group. And that's fine. We will work with it not being in a group just to show what happens. So we've got our design groups. We're happy. Let us analyze again. Static analysis. Again, notional horizontal loads and space frame. So when we come into design, and we are working to the Eurocode UK National Annex, we should have checked that earlier, and we go into steel member design, we'll see it suddenly goes bang and automatically creates all the design checks for us. It knows what's what, and it's doing this as one member, and it's showing that one there as not being in any group and therefore not automatically created. So that's another way of telling that I missed that member in those design groups. But there's no reason why I can't either add it to a group temporarily or go and put it in to the groups. So I should have an option to play with checks, change member groups. It was this one that I needed to get a member into, so we could search and do that, so we can come back and fix that, but I'm not going to worry about that. So these members have all now got these groups. So let's look at this one for example, and I can come in and do the singles design. Now the trick is, if you watch the screen, it's done a lot more than designing one member. It's designed all of these. So it's taken this single member check, but it's applied it to all of the members highlighted. So if I was to go to frame views and look at level 1 and then put that into a side view, and we would see that we're doing all of those members. If I was to look at, yeah, that's better. That's the orientation I would expect it to be in. And I can see all of these members are all checked the same way and checked out with the restraints at the point of load being applied or the columns coming in. So it's all checked correctly for the lengths, and we're checking all the portions. Now, having done that, what I could do before I move on to any other members, I could try and display the unity values, but it's not going to do that. And the reason it's not going to do that is because we haven't scanned. In fact, I haven't even designed that. It's just, well, we've just designed this one member. If I go scan for failures, just so that I can see everything, and then we'll do it on the whole frame, the whole design on the whole frame. And don't worry about the other members failing. I'm able now to look at this and get all the unity values displayed. And you can see that this member over here, remember I had the additional plant loading up here, is at 0.998, whereas these are 0.8686 and 803, slightly lighter. That tells me that possibly I could put that member as a different section size to these, so create it into a separate group and do it that way. And if I wanted to do that, what I would do is, the best way to do it correctly is to come along, go to design groups, choose the group you're interested in, so it's these, and do a copy so you get all the data, add a new group, and then apply these three parts into that group, and then you can just go paste all the settings so that all the settings are set as per. But that's now got its own design group. So if I go back into physical design, it's going to ask me to reanalyze because I had sections changed, and it knows that. Never mind the design groups. And we will see now when we look at this, it's not interested in that one. This one is different. So that one is 457 by 82. If I take these ones and size that as one group, we actually get a shallow, because we're in size rather than depth, sorry. So the 74 will work here as against the 82 here. So there's a bit of saving. The contractor might decide to make them all the same for simplicity, but there is that ability to suddenly review a group and say, no, actually I need to split this group into two and make another design group, as I've just done. So let's get back to the full frame, and looking at this individually, I can auto size every single member. Off it goes, and every single selected member apart from that one in cyan, which we haven't got a design group on or design check on, is now going to be designed. And we do our auto design twice, and remember we're sizing for weight. So very quickly, okay, so what we've got is all our members hopefully sized. I have done the design, and I'm now going to go and reanalyze, because there is some determinacy in the software. So it's going to reanalyze that with the new section sizes, and I'm now going to scan, and this will take very quickly, and it'll find any members that have, we've got one now so far that has failed due to transfer of moments and the redistribution due to this change in stiffness. And it's having jolly good think about the other members. 12 members now failing. So 12 members are now failing, and we can see that some of these members have now failed due to changes and everything. So what I can do is I can say auto size only the failing members. So auto size the members that failed. Off it goes, and it'll size up those 7, 8, 11 members. And it keeps going each time, and bear in mind a member could be one part of a whole group, so it's probably running through more than you think in here. So if I now go to the next fill, it should now, if I go and reanalyze, there we go, 15, 20, 30 cases, 40 cases, and just do one last scan, we should find that we still have one member failing, which could be of interest to us, and hopefully this time around we won't have the other members, although after member 120 there's something in there. There we go, we've now only got 2 members, 4. That's interesting. So where are the members that are failing is a very good question that we need to ask ourselves, and we're still up to those 11 members. Now it could be the bracing members that it's getting a wee bit tied over. So what I can do is I can turn on the unity values, but only the failing ones. So I can see where I have members that are failing. So we've got this member here outside for whatever reason is failing, and I've got some of the cantilever members, all these little cantilevers, and it's probably the deflection that's failing in those and nothing else. So this member is failing, and it's failing reasonably highly. So I am just going to manually walk up through the next sections until I get one that works. So 533 is what we needed to make that work. Let's look at our little cantilevers. These little cantilevers are the failing on deflection. Yeah, I thought it might be the problem. And the one thing I didn't do on my members was to set a deflection limit. So it is not very strict. It is a little canopy. It's not that important. I'm going to put a deflection limit of 1 in 100. So looking there, we're still moving. We're moving around 18 mil on that. So maybe we should think about increasing the section size. Anyway, a 203 by 133, let's move that up to a 254, and we're improving that slightly. The one area where it's difficult to reinterpret the deflections is when we have cantilevers. In ordinary beams it can reassess them for the changed section size quite easily. For cantilevers it is not as easy to do, but we are getting it still failing. And let's just check. First of all, it is a cantilever, yes, it understands that, and we're still getting that 18-19 mil. So if we open up Chrome, we can see the reason behind this rotation of the cantilever. If I go to this technical note on cantilevers, and if we look at this in a sensible resolution, we can see if we have a cantilever on a fixed base or on a knife edge, we end up with two different deflections of 14 and 34. So the rotation of the backspan is causing it to deflect by another 20 mil, and that's one of the reasons why our cantilever is failing miserably in deflection. It's because of the rotation of the span. Now if you look also at the different models, if you take a typical encastre 14, a beam and column all continuous, we're talking 25, and then the knife edge 41, and then simply supported it comes down to just the columns as 44. As you can see how significant these three, or in our case two, connecting members and their stiffnesses are. In our case the column is only a UC, whereas the beam is a haunched UB, and that's why we're getting such a large rotation. But bear in mind, a lot of that could be due to the rotation of the portal frame rather than the cantilever itself, so therefore strengthening it is not going to make a lot of difference now. So that would appear to be the such, and I'm going to accept that 20 mil as a satisfactory deflection. Now what I'm going to do next is to fix this check. So I can at any stage say I want to do a beam and beam portion on that member, so I'll add a new check in, and now I'm just going to size that one member up that we ignored. It's now satisfactory. So what we've got, other than one or two little failures that we were having a problem with, there's a column there that's ever so slightly failing, but appears not to be failing anymore. Appears to be okay, happy now. So if I go reanalyze and rescan for failures, we should find we have very little left in that. Now the next stage we have, so it looks as if by the number of them that it is all of those. Yep, that's failing. Now there appears still to be a little problem there, but I'm not going to worry today about that. So we can see that we can output for any level. So if I come out to planet level 1 and asked it display all the unity values, it's given me all those unity values. Happy days. If I ask it to put out the unity values that are critical for each section size, it's going to give you the most critical one for each section size. Bear in mind this is going to be used throughout all of those. That's on its own. This is going to be used for all of these. That's going to be used for all of these. So we are only getting a few values, and of course we can print that out to it and produce a snapshot for it. So that's the output and design. However, we now need to ascertain whether or not our design, our frame, is sway sensitive, and that requires us to do an elastic critical load factor check. And we can suddenly find that we have no P delta applied, we have no amplification applied of 1.3, 1.4, which is not something you normally do. So what we need to do is we need to apply this elastic critical load factor. Now you can see for these loading cases it's quite low and therefore significant, but for others that's quite high and it's irrelevant. 16, 18, 20 and 22 don't really need it, so it's only some of them cases that are needed. So what I'm going to do is now run back and I am going to go to Analysis, second order analysis, and I am asking it to include P delta using the Newton-Raphson method, which is the more rigorous method, and I'm going to apply it now. I could apply it just to the individual cases that were important, or I could say to all ultimate cases. So you're saying, but what about loading case 16 and the likes, which it didn't actually need it on? Yes, I could take it out, but it's not going to hurt it if it is such a loading case that the amplification factor is nothing, that the lambda crit is 16, 18, 20, 25, then P delta is going to have no effect on it. So you might as well just play conservative and apply the P delta to all of the ultimate cases and say apply. So now when I go to Analyze, Static Analysis, you'll see the P delta strapped onto all these cases. Off we go, and it's now doing a wee bit more work each time because it's doing an iterative analysis to determine the stable structure with the P delta second order movements applied. And there we go. So we go back into design, back into our steel member design, and that's going to allow us to reassess the frame with these additional forces. But there's no real worry. All we need to do is to scan for failures and see what happens, how many briefs come up as failing, and we should probably only get those couple of problematic cantilevers coming up. There we go. There's the cantilevers coming into play now. Again, it's only those cantilevers, and it's highlighting the deflection on those cantilevers. So the deflection on the cantilevers is going to be solved possibly not by putting this in as a massive stiff member, but stiffening either of these two. This is a determinate problem, looking at the end deflection due to the rotation. So the rotation of this cantilever is starting not at 0 but at a rotated value, which means it's again not as problematic as you think, because the whole cladding is going to be rotated due to the beam itself, the main beam. So we've now shown that we have no other failing members other than these ones. If I went to my little buttons, the critical values, and then only the ones that are failing, you'd see that it's not really happy. It's, I say, only those little end cantilevers that are unhappy about that problematic. There they go, those 3 on that side and 4 on that side. So there's a wee bit of a variation here due to the proximity of the additional loading. So I'm not going to worry about those cantilevers. I'm perfectly happy to accept those. One way to get around that is to come along and say, well, I'm going to accept 1 in 50, and therefore they don't no longer cause a problem in that situation. Cantilevers can always be problematic when they're not a cantilever into an encastre end. So we've designed most of it. What we haven't designed, we've designed the bracing, we've designed the beams, we've designed the primary beams with the restraints coming in at midpoints. What we haven't talked about is in fact the rafters up above the, and if I just zoom in, there were some default assumptions. The default assumption was purlins at 1.5 centers, because that's something we put in our brief, and if we look at it we can see lateral restraints at 1.5 centers. So provided we have 1.5 centers, we're okay. The only thing we haven't considered yet is this unrestrained length, and that is where the sister check called Appendix BB in the Eurocode, or Appendix G in the old BS codes. And I'm going to check the different portions, and in fact we've just put another portion in and we just need to make that a bit longer. Check that portion, say it's 4 meters, and therefore we're now checking that length, and we can see out to that over that 4 meter length it's not happy, and it's actually this length here, because it's actually starting from here and going that direction, so it's up at the apex that it's not happy. Down at the eaves it's got more flexing from the column, which is in fact a UC, and that's why it's causing this to rotate. So what we need to do is to put another restraint in there and say, well, actually we would have a restraint and put one in here at 2 meters, and then do another 2 meters, and see that we actually get away with one intermediate restraint, proving that we can get that to work with that intermediate restraint. We also in reality need to do the same down here, because if you remember, this is part of a continuous beam, but you'll see when we look at it that it's not along Appendix G. And did I put an Appendix G onto this? I don't believe I did. So we only did this as a axle with moment. So I'm just going to put in a manual Appendix G onto that, and yes, over its full length it won't work. But if you know what length the member is, you can say, well, let's put it at 2 meters out, and you can show that the 2 meter length down to the point of contraflexure is not a problem. And it never really is a problem in these loaded beams like this with the shortish spans. So we don't really have to worry about it. You know, frequently what you do is you say, what's the length of that member? And I think it's roughly 4.5 meters. Well, there's no reason why you can't say 2.25 and then 2.25, and that gets you 2 checks, one at either end. It's 2.2. If I type properly, I get the right answer, and you can see we've done a rigorous check then at both ends to make sure that there's no problem from the Appendix G. Now on the other side we get a longer length, so if we look at this one, it actually shows you that out to the point of contraflexure we don't have a problem. So again, we're okay. We don't have to worry about those. But it's important just to check those. Now, do you remember I talked about the bracing? The bracing members have come in, and it's come up with a 90 by 12, and it is tension only. And we'll find that it is not a problem. And we will see that under this, we will see that we're taking out the holes and we are not losing enough of the member. But personally, I don't like a 90. I would much rather see 100 by 10 and make sure that it works, because you're going to be losing a reasonable amount. You're losing that amount out of the 10, so you're losing a net, which is 5.6 centimeters squared. So you can see you've actually lost 44% of the gross area on that in tension, and that's why it's important in those members. The other thing is, for the bracing I use 275 steel because I find that that is better. For flats normally don't come in the 355, because let's face it, trying to handle them at those higher stresses, if they were that flimsy, they'd be buckling all over the place. And again, you don't want these elongations to be too much, so that lower stress steel is better, because you want to keep the stresses down, because the higher these worked at utilization, the longer the elongation and the more the whole frame moves. which is not what you want. So in reality, you should be thinking of taking a limitation to pull down. You make your bracing when you work at 30% stress, not at 100% of stress. Okay, so we've done that. We have reviewed our elastic critical load factor and found it now to be satisfactory, and we've confirmed everything, and there we are with our design. So we can now print this out. So output is very, very important, and if I do this logically, I'm going to go and view planet level 1. I am going to come back to the normal members, thank goodness, and I'm going to turn on my Unity values, and I can then say print that, and I can say print to printer, PDF creator, and it's going to take that and print that out. I can then come up to the next level and print that out, and I then go up to the next level, level 2, and I get the values again, and I can go print graphics, and possibly landscape might have been better than portrait, but I'm doing portrait. In this case it works fine, and off it goes, and it's doing it in the background. And then you would come along to your roof plan, and you would do the same. You'd probably actually even get away with, in these cases, because it's so symmetrical, just doing half of the frame and print that out. Print graphics if you wanted to, you know, and that's going to give you those values, and then you can do the same. So those summaries are quite useful. But what you can also do, coming back to the full frame, there we go, turn off all that, is we can go down and say, right, let's give us some printed output, print design output. Okay, it's suggesting we should change or reanalyze, but I'm not going to. I'm going to say I want to include all members, but only the critical portion in each member, and only members above 0.75. So it's going to run down through all of the design checks, every single one, and it's going to highlight all the ones that are problematic, and it's going to highlight any that are above 0.75. But for each member it'll only give me the worst check. So for my big rafters up above, it'll give me the worst Appendix G, probably on the first portion or the second portion. And it's walking down through all of these design checks. So here we go. These are all the members that's highlighted that are above a certain value. I can now say print that summary and print it to my PDF creator in this case, and it's gone off and it's now giving me 13 pages because there's quite a lot of design checks. And I am going to say above 0.95 now, and only the critical section, and I'm going to go, and it's just going to walk through and auto select those again, and it's going to give me a lot less members. So it's giving me 1, 2, 3, 4, 5 critical members that are very high, and I'm going to print the full design checks on those. So I'm going to take those 5 members and print in detail the design checks. So that's all the design output done. I'm now going to just close that document and have a look at what we give you. What did we give you? We just say OK, and here it goes. So if you remember, the detailed output, nice and clear, telling us that it was frame and geometry, plan view, planet level 1, and then we have, in this case, planet level 2, and then part of the roof, and then we have this summary that we took of the physical numbers, what it is, the length of the members, how we checked it. As you can see, for some of these members then down below, these are the ones for the roof. You have 1.5 to 1 to 3 meters, 3 to 4.5, so between the purlins, all there, and you can see all the highlighted ones above 0.75, and then finally we come down and we actually do the detailed design checks for 1, 2, 3, 4, 5 members. 6, I think. There we go. So 5 or 6 members, I can't remember how many. So that's all been output for you, ready to work into your report. So all dead easy. So that's really going through the whole process from analysis to design. What I'm going to do now is look at 2 additional aspects. One of them is connection design. So design steel connection design groups similar to the member design groups. I've created base connection design groups. I've created others as well for the rafters, so I'm happy with all those. I go into design and steel connections, and it's asking me to reanalyze the frame because remember I'd changed the section sizes. It's going to take a second or two. So here we are, we've got a beam designed. I'm going to look at a column, and there's a little shearing force that's going to be augmented, and you'll see here for this it's saying it's actually not just that one but those ones as well. So all of those members are all in the same, and it's saying yep, we've done that and we found all these matching joints. So we're giving a design loading cases. We return back down to 1, 2, 3, 4 for the second joint, the third, fourth, fifth and sixth joint. So when we do an auto design, it's going to look at all those loading cases for all the different assembled members and do those all in one and give us our design. Now when I go in and look at my beam to column flange joint, I'm going to apply this. In fact, zooming in, if I can get it, here we go, we're going to apply that. That's probably an easier way of working with it. And we're going to apply it to this member here. So I'm going to say apply that to this rafter. And it said, yeah, that one, that one, that one as well. And it's found a little add-on and it's going to do the design on that and do my design simply. So in my steel design, I can also do connection design, integrate it from the frame analysis. Or I can do my base forces, I can do my connections for my eaves, ties and everything as well. So I've got full flexibility of integration. So having done my design, and I'm not going into this connection design in detail because it's not really what this has been about today other than showing you that we can do it. I am going to take this model and I'm going to fire this back to Revit. So I am going to go to my Revit Link manager and I am going to save and submit the changes to the link, and we can even export analysis results if we really wanted to. And then just minimize that, go to my Revit model, which was called Project 1, and open Revit, and here it comes. Hopefully with our original section sizes. Yep, it's got all the standard original section sizes, which were all standard. What I'm now going to do is go to the add-in, the link manager, and I am connect to existing. We already have a link here, but we'll reconnect to it and open. Yeah. Update model from the link, and off it goes, and it's going to change a lot of section sizes because we've now going to design that. You can see original was 203, revised is 133s, likewise, you know, all over the place, and I'm going to say OK to all of that, and it's going to now update all their section sizes, and you'll suddenly find all of these sections changing in the model. So it's doing quite a detailed updating there of several hundred members. So here we go, and you will see now we've got the revised sections into the system with the revised section sizes all built in to the model for us, and it's a lot thinner sections on the columns there. That's the 152 rather than the 203s. These are now 45779, then you should find then that this one, or 74, this one is the 533 by 74, which brings me to a different topic, but very, very important. The cantilevers or tapered members, dead easy. If I take a section rather than loading and I choose a member, I'm able to do haunched and tapered members. The default is uniform, but I can have two types of haunches, which first one is a single haunch, so it's uniform, taper, uniform, and the second one is taper, uniform, taper. Now I chose the uniform, taper, uniform, and I just said that it's 0 and 0. Now, because I asked it to do the depth as 0.5 and 1, it's never gone above the serial size and therefore never introduces that third flange. If I choose that depth to be 2, then you would end up with an additional. So it's saying, hold on guys, we've got a section that starts from serial and gets bigger, therefore we have the additional middle flange. Whereas if I'm going down below 1, it says no, we don't have the middle flange, and I put that back to 1. So that's how we do the haunching. It's very straightforward. The lateral restraint of the Purlins, I mentioned that if I go into the design groups, it's worthwhile talking that over again, looking at most of the members we just said 1L, but for the rafters here it's 1L, but then we've come down below and said, but we want to then look at portions at 1.5 meters apart. So we're assuming that the Purlins are at 1.5, and then we do the Appendix G to find out where we want the stays. Can we get one-way load transfer to Purlins while using FE analysis? Well, this isn't FE analysis as such. Obviously all analysis is an FE, but everything here is member, beam elements rather than block elements and slab elements. The only variation in that is for the semi-rigid stiff deck uses a little FE in the background. If we're dealing with full FE analysis, then you could do transfer from that onto the Purlins. How did I create connection groups? Again, that's very straightforward. Same way we do the steel, we can just say connection groups, and we can say, right, I want to do, we're going to call it Fred, and we want to do a beam splice on, and then you want to apply it to that member and that member and that member. So you're then grouping those all together, and they will not just take the forces out each time from each, they will look, as long as they're the same section size, they will do them all together. And we can also in here, because connections can get a lot of silly loading cases, we can say we'll actually ignore cases of less than 2% error. If there's within a 2% variation, just use the first ones you found, and that's how you would do your connection design groups. You put the name, you select the type of connection, and then you select the members. Very straightforward. So that's it, ladies and gentlemen. I have already loaded up the sample files. I'm just looking for Chrome onto our website. So if you were to go onto our website, you could download our example file. So you will see Steel Design Webinar sample file is available to download and play with yourself. But I will thank you all very, very much for attending today and wish you all a good day. Thank you.